Hello, this is video 2, work is force times distance. And take note, before you watch this video, you should have already watched the first video in your class. And you should have also completed this example problems right here, the one with Antonio and the one with the car. And you should have also completed these 4 practice problems. If you haven't done that, it was your homework, and the answers were at the bottom. So make sure that you get those problems done. Now we're going to move on to work is a force acting over a distance, and there's going to be some more notes, and then a couple of example problems. So here we go. The first thing I just want to bring up again is that there were 2 different formulas for work, and one of them was work equals change in energy, and the other one was work equals force times distance. So these 2 formulas. Previous examples were using this formula, and so were the 4 practice problems also using that formula, work equals change in energy. So we're going to do some examples with work equals force times distance. But before we do that, I want to give you guys some conceptual notes and some more information about the types of forces that do work. So, ready? Here we go. Not all forces do work. So this is something definitely important. Not all forces do work. Work can only be done if an object is in motion. So take a second to write that down. Work can only be done if an object is in motion. And then a second key point is that work can only be done by a force acting along the axis of movement. No perpendicular work. So what that means is if an object is moving to the right, a force acting to the right could be doing work. A force acting to the left could be doing work. But a force acting up on the object could not be doing work. A force acting down on the object could not be doing work. So that's what this key point means, that work can only be done by an object acting along the axis of movement. This key point here, work can only be done if an object is in motion. So just for example, let's say I'm a stick figure and I am holding up a yo-yo, and my yo-yo is a square. So here I am holding it up. I'm just holding it. Am I doing any work? No, I'm not doing any work because my object is not in motion. Am I applying a force? Yes, I am applying a force to hold up the box. But since there's no distance to multiply using work equals force times distance, since there's no distance, there's no work. Alright, so just some more visual examples using stick figures. These forces shown are not doing work, so no work is being done here, no work is being done here. And what I would like for to happen right now is to just pause this video and discuss why are these 2 pictures examples of forces that are not doing work. Go. Discuss. So, these are not doing work because the force applied on this box is up and it's moving to the right. Up and to the right are perpendicular, and perpendicular forces do work. This guy, there is no motion here. I imagine that this person is probably holding a door closed or pushing against a wall, maybe he's stretching his foot, something like that. He's not doing any work by this force that he's applying against the wall because the wall is not moving. So if you were to do work equals force times distance, There's no distance, there's no work. Examples. So this is an example of a conceptual question. I would ask that whoever is controlling the video just pause this video for about a minute so that people can read the different options and choose the answer, whichever answer. Okay, so I'm going to read through these and come to my own conclusion here. So you should have already talked about it. Which of the following examples is work performed? So we're looking for work being performed. Rain falls from the sky. Okay, so rain falling from the sky is probably going to get faster and faster and faster, right? So it's going to have an increase in kinetic energy. So work is being done here. Work is being done by gravity, which pulls it down, and work is being done maybe by air resistance, which pushes it up. Both of those up and down forces are acting in the direction of motion because the rain is falling down. Up and down are along the same axis of motion as down. Okay, Gael holds a 50-kilogram barbell. He's just holding it. So work is not being performed. There's no work because there's no motion. Pedro lifts a bag of groceries. So if he's lifting it up, he's applying an upward force, and the direction of motion is up. So up and up, those are in the same axis of motion. So work is being done. Okay, Mr. Cabley pushes a car that will not move. Okay, if it's not moving, then the distance equals 0, and therefore there's no work done. So no work is being done here. So which ones had work? Number 1 had work, number 3 had work. So the answer would be H. Moving on. Okay, which of the following is the best evidence that work has been done on or by an object? Okay, pause the video for about 30 seconds to get students time to look at the answer choices. Okay, which of them is best evidence that work has been done? A, energy is the energy of the object has changed. Okay, so I'm seeing delta E, energy of an object has changed. I'm going to keep that on the back burner. Velocity of an object remains constant. Okay, well, if it has a velocity that's remaining constant, we definitely know that its kinetic energy isn't changing. But do we know anything else about it? Not really. We don't know anything else about it, so we just know that the kinetic energy is not changing. The mass has not changed. Sorry, the mass has changed. No, I don't think that that's evidence of work being done. Okay, D, the direction the object is moving remains constant, meaning it doesn't change directions. I don't think that that's any evidence for work being done, so I guess the best choice was A, that the energy has changed. Okay, a calculation question. A total of 750 joules of work. Okay, so work is 750 joules. When a force of 125 newtons, okay, force is 125 newtons, is exerted on a box to move it. How far was the box moved? Okay, how far? That's asking for distance. So if we use work equals force times distance, 750 equals 125 times D, well then D will be equal to 750 divided by 125, which is 6 meters. So how far was that box moved? It was moved 6 meters. Alright, so those were some examples, and then some more examples. So this will be the Next example, a force of 650 newtons pushes a car over a distance of 15 meters. How much work is done? Well, and then there's a second question, how much will the kinetic energy of the car increase? So, how much work is done? Work is force times distance. So that would be 650 newtons times 15 meters. Very straightforward question. Just multiply 650 times 15, 9,750. So the work done is 9,750 joules of work. And then the follow-up question, how much will the kinetic energy of the car increase? Well, if work is change in energy, maybe specifically in this case work is change in kinetic energy, then the kinetic energy of the car would increase by 9,750 joules. So the work represents how much work is done and how much the kinetic energy of the car will increase. Next example. A car originally has 1,500 joules of kinetic energy. So I'm going to say that's K original. 1,500 joules. A force of 100 newtons acts on it for a distance of 3 meters. So I can already tell that my work is going to be force times distance. So 100 times 3, that's 300 joules. So my work will be equal to force times distance. What kinetic energy will it have after the force acts? So I guess what it's asking is for kinetic energy after, which is K final. All right, work means change in energy. So what's happening here is we're applying both work equals change in energy and work equals force times distance together in the same problem. So here, work will be K final minus K original. So 300 joules is equal to K final, which is what we're looking for, minus K original, which is 1,500. So to get K final, we'll add 1,500 to both sides. And we'll get that 1,800 joules is the final kinetic energy. So what happened here? The kinetic energy of the car increased from 1,500 joules of original kinetic energy to 1,800 joules of final kinetic energy. So looking forward to what other types of questions can you ask if you have both of these two formulas for work? An example of an example. A car of mass m accelerates from VO to VF over a distance of d. What force acted upon it? So, like, I could ask you what force acted. What you would need to know is work equals force times distance, and if you're looking for the force, and you're given the distance, you need to calculate the work. How would you calculate the work? Well, you'd calculate it by doing K final minus K original. So you'd use the VO and the VF to calculate kinetic energy F and kinetic energy original. You'd subtract those two to get the work. You could use that work, divide by the distance to get the force. And so this type of problem will be in your practice. So that's actually the next thing that you guys are going to be doing. So there's additional practice problems below. Go ahead and do those, and those are your assignment for today. Have fun.